So we had phase speed, 2 pi over lambda. So this is the wave length, or 2 pi over it is the wave number. And then we have 2 pi over lambda over here, so there's a wave number in there. And then here's a frequency with a 2 pi, so this is a true frequency. And then we have an angular frequency. There are massive different ways of writing it. Some of them are more convenient than others. I just want you to have a sense of what frequencies are like and periods are like, so the time variability side, and then wave numbers and wave lengths, the spatial side. And whether they're the 2 pi's or not, it's better not to get used to any particular standard, but to kind of think it through every time. The phase, the thing that's up here, needs to go from 0 to 2 pi every cycle. And whether it's 0 to 2 pi in space or 0 to 2 pi in time, you can think about whether you're sitting still at a location or whether you're measuring crest to crest to crest. Okay? And then the next, so the phase speed, this c that's sitting up here, is omega over k. So it's the angular frequency over the wave number, or you could actually write it as the wavelength over the period if you convert between these things. So it doesn't matter which definition it is, but this is the easy one to remember when we're thinking about whether it's a dispersive wave or not. Because this one, the group velocity, is the derivative of our equation for frequency with respect to k. So if these two turn out to be equal, then the wave doesn't disperse. Okay? Sorry, now I've filled in a few more down here. Okay, so the main dispersion relation we talked about last time was a non-dispersive plane wave, which is where we have omega squared equals some speed that's constant, or at least a constant with respect to k, times k squared. And so this would give you two, if this was just an x, all in a one-dimensional wave, it could go either in the positive x direction or the negative x direction if you solve for this. And how can I tell that the phase speed and the group velocity are equal? So what are my phase speeds in that? Phase speed is omega over k. So what's that? How do I get omega out of that one?
C0 plus or minus C0.
Yeah, it's plus or minus. That's the part I was trying to get at. Is so this is squared. So if I take the square root, it turns out to be plus or minus C0 times k. And if I divide that by k, it's plus or minus C0. So I could go either towards positive x or towards negative x in time with this dispersion relation. Okay, so what about my group velocity? That's partial derivative of omega with respect to k. So if omega is equal to plus or minus c naught k, what's the omega be k? Plus or minus c naught. Plus or minus c naught. So in this case, these two are equal. So it's not, the wave doesn't disperse. But we're going to see some today where that's not true. Okay? Okay. So a key distinction when we're thinking about water waves is how deep the water is. And there's a reason why, essentially. So if we imagine that we have a surface displacement, so at the top of the wave, if the wave is propagating that way, the top of the wave is moving this way, the bottom of the wave is moving that way, and so it's piling up right here because it's combining velocities from either side. So it'll start rising right here as this part of the wave is going down. Does that make sense to everybody? There's a convergence between this velocity and this velocity, and then there's a divergence between this velocity and this velocity. So this part is going down towards the trough. The trough is coming up, and so it's moving to this direction over time. And we said last time that that's really made up of these little orbital velocities that are underneath. And it turns out, as we'll see in a second, when you try and solve for how this kind of wave works, those orbital velocities decay with depth. And the decay length scale is related to the wavelength. So really, really long waves don't decay very quickly in the vertical. They decay slowly. And really, really short waves decay very fast. So you can imagine thinking about the situation where you have a wave and you have the bottom. So if I compare the wavelength to the depth, if the wavelength is much, much longer than the depth, then this decay won't have much time to happen. And so the orbital velocities would be more or less constant from top to bottom. That's called the long wave limit, or sometimes the shallow water limit. So the key comparison is the depth. The depth versus the wavelength. So if the wavelength is much, much bigger than the depth, so if that's less than 1, that's shallow water. Or long waves. And it's much, much greater than 1. That's deep water. Or short waves. Okay. So all the other pieces we've seen so far. Okay. So here's where we get to a little bit of math. So how many of you have done like a geophysics class on seismic waves, like P waves and S waves and all that stuff? Okay. I will just say this is a similar sort of flavor to that kind of thing, where you just assume that the velocities, those orbital velocities, are irrotational. They are, which means that you can write any velocity field as a part that has a potential and a part that has a stream function. And we talked a little bit about a stream function before, but this is kind of like, this is a general calculus trick. And if I forget about this part and just say that's not part of the wave, which is what people really do. They don't prove that that's the case. They just say, forget about this part. That's the vortex because it's rotating. Let's talk about the non-rotating bit. And let's think about what kind of wave that supports that, which is the same process that they do in seismology. What?
Sorry, I thought we just saw that they rotate.
So this is yes, good question. Okay, this is not about the velocity at a certain point, which we were saying it's rotating in time. Sometimes it's going up, now it's going over, now it's going down, now it's going back. This is about the spatial gradients. So is the velocity, does it have a curl or does it have a divergence?
Okay, so the wave as a whole can't rotate.
Yes. So the wave isn't like, doesn't have vorticity is the way to think of it from how we've talked about it. So that's really normally just an assumption. Suppose the wave has no vorticity, okay? And if it's also divergenceless, then this guy doesn't have to be, so the stream function is 0 because we said it's the vorticity is 0. It could, let me just gotta say this. Sorry. It is possible to say that this has both no divergence and no rotation. So it is a special kind of wave. And if you plug that in here, what that says is that you have to solve this kind of an equation. So let me do that out. It's kind of a cool trick. Okay, so U equals the phi dx minus d psi dy dz. V equals d phi w plus d psi dx. Okay, so what, if that's true, and then I say the divergence of the velocity equals 0, what does that mean? So how do I get the divergence of this if v is 0? So it's just u's and w's. Right, so this means du dx plus dw dz equals 0. So let's do that. What's du dx? It's del dot u equals second derivative of u of phi with respect to x, and then minus the second derivative dx dz of psi, and then we do the other one, so ddz of w, second derivative of phi dz plus second derivative dx dz psi. So the two psi parts cancel out. So whatever was making it, if we had vorticity, if we had stream function, it doesn't appear in this divergenceless part anyway. So let's just pay attention to what this guy has. And we can just assume the stream function is 0. That's some other part we're not talking about. So what kind of an equation is this? If this thing equals 0. That's this kind of an equation. So this is the Poisson equation. So does anybody know any properties of solutions to the Poisson equation? So you can make it with sines and cosines in one direction and exponentials in the other direction. It's a really common system. But the most important property is that it can't have any internal extrema. So whatever the value of psi is on the boundaries, it can't make any more extrema, maxima or minima, inside the boundaries. So you would say, well, if it's 0 everywhere and it has no extrema, and then on the boundaries it's boring, like phi is equal to 0 everywhere, then yeah, it is boring. Then the answer is 0. But what's interesting about surface waves, and this is true of all surface waves in all media, not just water, is that you can put an interesting boundary condition at the top that has to do with the motion of the boundary. And then this guy might be non-zero along that interesting motion and then decay as you go in. So when we see this, that's exactly what's happening. We have an interesting boundary condition going on up here to do with the free surface, and then there's no extrema in the velocity. It's decaying away from the surface, but it's doing it with a specified rule. Does that make sense to everybody? A little? So that's the way to understand what this means. It says no extrema in the interior, but then we need an interesting boundary condition to make the waves do something interesting. And the real assumption here is that, so this is one of the things that you will frequently hear people say wrong. There's motion here, but this field is divergenceless and irrotational. There's no vorticity and no divergence, but it's still moving. So how is that possible? Well, it's possible because this can have non-trivial solutions, even though it doesn't have any internal extrema, if you have interesting boundary conditions. Do you have a question, Akash? Yeah.
I thought u was just d phi by dx or minus d psi by dx.
Oh, you're talking about this, the stream function part?
Yeah.
No, it's both actually. So it's the curl of stream function is equal to the 3D velocity. And so this stream function that we're talking about is the component that's coming out of the board, and it's in the y direction here.
So I'm just confused because any 2D velocity.
Yeah, any 2D velocity.
But this stream function is 3D.
Sorry. Yeah, but I'm thinking of the y component of that stream function. So I could have other stream function. I could have a stream function in the vertical, which is like the gyres, like we've been talking about. I could have a stream function in the other direction, like the overturning circulation. But this is sort of a small scale one. And on the plane of the waves, we don't think there's an overturning stream function overturning along the crests of the waves, because that doesn't make any sense. And we don't think that there's one that's taking the crests and wrapping them around in a circle. Although that one actually does come in the rotating case we talked about at the end with the Coriolis force. But we think that the main one would be like overturning in the direction of the waves, like the little orbital motions. So the stream function we're thinking about is the stream function whose axis is aligned with the wave crests. Does that make sense? So it's one component of the stream function, and that's this one. Okay, so here's some boundary conditions. Here's the equation. So at the bottom, we have a flat bottom, but we just set the velocity to 0 at the bottom. So the water doesn't go through the bottom. That's good. At the surface, there are two different conditions. So if the water is bouncing around and there's an atmosphere above it, and the atmospheric pressure is constant, or we can just totally neglect the atmospheric pressure and say it's effectively 0, it's not driving the water, then that's one condition. So there's a pressure condition at the surface. And then there's also a sea surface height evolution in time equation. So if the sea surface height goes up, there has to be a vertical velocity to do it. If it goes down, there has to be a vertical velocity to do it. And so that's this equation, which is the rate of change of the sea surface height following the motion of the water is the vertical velocity evaluated at the sea surface height. Okay? So that's kind of what these little, what I was saying is if we wanted to lift this up, we'd have a vertical velocity there that would be lifting the wave up. Does that make sense? And it would be from convergences nearby. Okay. So, all right, this is still a little bit crazy, and only this one depends explicitly on this phi. So how do we get pressure in phi? And how do we get eta in terms of phi? And how do we write W in terms of phi? There's a lot of messy things. And this one is a material derivative, so what do we know about the material derivative? It moves around with the packet and it's nonlinear. So we have a really beautiful, simple linear field equation, but our boundary condition is nonlinear. So the way to think about this is to think about the hydrostatic pressure in that little anomaly, or to think about how the pressure accumulates, I guess is more. So this guy looks a lot like the hydrostatic balance. There's a d phi dz based on the surface height. This guy really is, this is g eta. So this is the hydrostatic part, but it's not matching a pressure, it's matching a rate of change of something. So this is like in the vertical acceleration equation, you can make some of this stuff, some rate of change of W, essentially, by having the sea surface height high. If it's high, it wants to fall. If it's low, it wants to pop back up. And so these guys are a linearized version of these two systems. So I don't want to go into the details about how that is. It's just to say that we have pressure matching at the surface, and then we have velocity matching at the surface. So we're not letting the parcels at the surface fly away. The vertical velocity at the surface matches the up and down of the surface. And the pressure, this looks a little bit reminiscent of something like a hydrostatic pressure. It's not actually a hydrostatic pressure, but it's the same kind of thinking of extra sea surface height makes pressure underneath kind of thinking. Okay, and the other thing that happened was before we had the extra complication that both of these were evaluated at the moving sea surface height, which is a total nightmare. When we go to this approximate system, in interpreting how the eta relates to that, how the pressure accumulates in that little tiny layer at the top, we can reevaluate the boundary condition at the still water level where the waves would be if they weren't moving. And the same is true of this one. So this one is a linear approximation to the real one. This one is, I think it's actually the real pressure equation, but it's reevaluated at z equals 0 rather than right at the surface. Okay? Sorry, I know this is a little weird. But the main point I want to make here is we've got this equation, and now we've got linear field equations that are specifying something about this phi. Either its derivative or its time derivative at the boundary, and the variable that it depends on is either 0, it's just the location of the boundary, or the present sea surface height or its sea surface height rate of change. So we've got exactly that. We have this boring equation in the middle that says no extrema happen, but on the surface, if the sea surface height is doing something, it's driving interesting variations in either the derivative of phi or its time derivative at the surface, and that's going to propagate a signal down into the interior. And so you plug in a big exponential and you find the solution, and the solutions look like this, where they have coches and senches and complex exponentials. This is basically something that's decaying exponentially in the vertical, so that's not so surprising. It's a cosh of z, and it's oscillating in the horizontal. It's wave-like in the horizontal. And look, it has the same k squared and l squared in the vertical decay that it does k and l in the horizontal wave. So the wavelength and the vertical decay scale are linked together. And they're linked together because when you plug them into this equation, they have to cancel out. The double derivative of x and the double derivative of z have to cancel each other. Does that make sense? I can write that down quickly if people want to see. Let me write it down. It's a little. So, what if I guess that phi equals e to the ikx plus mz? If I just assume that there's an exponential form. Portion. What do I get if I plug that into this one? Minus k squared phi. So it's minus because there's an I. And then I get two k's, one for each derivative. And what do I get when I plug it into this one? M squared. And phi goes away as long as it's not 0. So as long as there's a wave, you can cancel that out. So that says k squared equals m squared. So the decay in the vertical is equal to the complex part of the horizontal bit. So it's linked that the wavelength and the decay scale have to match up to each other. Does that make sense? Okay, so that's what we meant by shallow and deep, is exactly this kind of thing. Okay, so staring at the full solution now, sorry, it's got k's and l's because it could go in the x direction or the y direction or some combination, and it's a little messy. But anyway, and now there's an I sigma t, and sorry, sigma and omega are the same thing. I grabbed these equations out of a book that likes sigma instead of omega for the angular frequency. I'm trying to be consistent on notation, but that one's different. Okay, so here's what the solution looks like. If you plug it in, back into that equation and try and enforce all the boundary conditions, it gives you a constraint on the frequency, sigma or omega squared, and the k's and l's, and the depth. So let's write this out without the k squared and l squared bit, just to make it a little simpler. If I forget about the y dependence and we just say we have a wave in x, it's omega squared equals k squared, no, gk, tanh kh. G, no, I just set L to 0 and take the absolute value of K, GK, tanh K times H. Okay, this looks kind of ugly. What's the phase speed of this? Some horrible thing, right? It will be square root of G over K, square root of tanh KH. Right? Not very helpful. So, but what do we know about tanh? What does that function look like? This is like blast. So at very far from 0, what does tanh go to? Should I write it out? It goes to plus or minus 1 at infinity. And right near the origin, it looks like a line of slope 1. So let's not worry about this one for right now. Let's make an approximation. What does this look like when KH is really, really big? It means that this goes to 1. So omega squared equals GK if KH is really, really big. What's KH being really, really big? What kind of a wave is that?
Deep water.
Deep water, because H is big, or short, either way, because K is really big. So we can think of it as both. Or in units of wavelength, the depth is much, much deeper than the wavelength. And what's the other limit? Omega squared. What if GK is really small? Or KH is really small? What happens? Then it tanh becomes something with a slope of 1. So it has this, it's just equal to whatever's inside. Let's put it a little bit approximate. Then we get GK times K times H if KH is less than 1, which is equal to K squared times C naught squared, where C naught, sorry, I'm out of room here, C naught is equal to the square root of G times H. So what kind of a wave is this? Shallow water wave, so it's, or a long wave, that's true. But what about this omega squared equals K squared C squared? It's a non-dispersive wave. And it's a non-dispersive wave with a special phase speed. The phase speed and group velocity in this case are both square root of G times H. So shallow water waves are non-dispersive. Deep water waves are dispersive. Okay? And the real waves are definitely dispersive in some elaborate, complicated way that is hard to think about. But we know that these are the two limits that it goes to. So here's the real one. So let's look at some pictures of shallow water waves and deep water waves and think about how they look like. Okay, so if you were to draw the velocity field underneath a wave, this is what it looks like. So it has upward motion where the crest is going to be next. So all this convergence here is lifting up the surface. It's actually, there's no convergence because it diverges this way, but the water is all moving towards that part and pushing up the surface right there. And when it pushes up the surface, this will be a crest later in time. And this part that's at kind of neutral height right now is going downward, following these velocities. Velocity goes down, it can run along the bottom but not through the bottom. And then on this side, this one is going down, which is the same as this part. So it's going down, this part's going up. So the crest is soon going to be here, the trough is soon going to be here, and this side of the trough is going to be going up while this side is going down. Does that make sense? And you can see that, so this is the complicated boundary condition, the one where we set that pressure matching to the surface, and also the d eta dt was equal to the w. So see how complicated the w is, and the d eta dt is where that surface is going next. It's a pretty elaborate thing. Down here, the boundary condition is pretty simple. It's just no flow through the boundary. And in between, there are no extrema. We don't see any velocities that are bigger in the middle than they are at the surface. They all tend to decrease in intensity away from the surface. So, if we have a really deep wave, that decrease away from the surface means that we just don't have any flow at the bottom, and we have a lot of decay. So this is a deep water wave or a shallow wave, which means that k times h is much, much greater than 1, and the flow doesn't make it to the bottom. Okay? If we have a shallow water wave, basically the flow is the same top to bottom. It's just sloshing around in a circle. There's not much room for it to decay because the wavelength is much, much longer than the depth. And if you're somewhere in the middle, you get this kind of elaborate touching the bottom and also decaying piece, which is where that complicated tangent comes in. Okay, so if we wanted to do more calculus and really take a lot of derivatives, we could take the derivative of our square root of this and prove to ourselves that this is actually the group speed, the group velocity that goes with this phase speed. But let's just look at them side by side and see what it's like. In the limit where this is g k squared h, what's this one? Sorry, so this is this guy, the non-dispersive one, kh much, much less than 1. So if kh is much, much less than 1, what's the group velocity? C. So this one is 1, that one's easy. This one is 2kh over sine of 2kh when kh is close to 0, which means that sine becomes its argument. This guy equals that guy. It's 1 here. So 1 plus 1, so it goes to C. But we knew that anyway because it's a non-dispersive wave. We've already argued that. So it's non-dispersive, which means that CG equals C. So in that limit, we get 1 plus 1 here. What's the other limit? What if KH is much, much greater than 1? What does this go to? Does anybody remember what century it is? This is like, whatever, going back to trig in whatever, 10th grade. So the sinh of x is e to the x plus e to the minus x to this minus over 2. So if this argument gets really, really big, what does this thing go to? Infinity. Yeah. Does it go to infinity faster than x does? So it's x over e to the x for large x, right? Which is 0. So this goes to 0. So then the group speed is what? Yeah, c over 2. So that's really weird. And then it's dispersive, but it's dispersive in this funny way where it has the same, it's proportional to the same speed, it's just half as big. So the group velocity is half as big as the phase velocity, as the phase speed for deep water waves, and they're equal to each other for long water, for shallow water waves. And do I have the? So we just went through exactly this, and sorry, I don't know why I switched to these because I'm stupid. But anyway, that should be c. So the group speed, the group velocity equals 1/2 of the phase in the deep water case, and in the shallow water case, they're equal to each other. So think about our wave packets from last time. So we had a wave packet that had an envelope that was moving along with the group velocity, and then there were crests and troughs inside. What does this say about who's going to win? The crests and troughs or the envelope? The crests and troughs are going to go twice as fast as the group. So we should expect to see a crest appear at the back of the group and overtake the group and then disappear in the front, just like we saw in the video, which I hope I have. Oh, I do. Ha. So this is the deep water wave dispersion relation. So here they come, moving towards the front, and it's hard to tell that they're going twice as fast, but they're going twice as fast. Okay? So these are some very weird. This is like if you really were insistent that you wanted to know periods and frequencies. We can skip this. This is a crazy thing. Except it's easy to observe. Okay, so let's watch some of our movies again. Okay, here's gravity waves. Now, 2 different wavelengths in deep water. So what can you tell me about the group speeds of the 2 different wavelengths? Group velocity, group speed, whatever. Which one? Which one's faster? Short waves or long waves? Long waves. So how do we get that from this equation? Omega squared equals GK. How do I get CP and CG out of that?
W over K.
Yeah, omega over K. D omega dk. So what's omega is the square root of dk. So this is the square root of G over K. Right? Because it's the square root of GK divided by K. And this one is what? Square root of GK, the derivative, which we could think hard and be like, wait, what's the rule for taking the derivative of a square root? Or we can just remember that it's 1/2 of that one. And then we've already proven it, so we can just write it down. Okay? All right, so which groups go faster, the long ones or the short ones here? Long ones have a big or a small k? Small k, small wave number, large wavelength. So when this is small, the group speed is big. So that prediction is correct. This one is always smaller than that one. So in both the short waves and the long waves, the crests and troughs should overtake the packet, should overtake the train. So here we go. These guys are disappearing in the front. That's good. And these are going towards the front too. Okay? And then if we do the same initial condition for the shallow water waves, we get this bizarre situation where it doesn't evolve because it's not a dispersive wave. Okay? So we have dispersive waves in deep water, non-dispersive waves in shallow water. They come from that complicated surface boundary condition and the kind of simple field equation inside. And pretty much it's the distribution of the velocity field, so the velocities don't pile up, don't have a divergence, and don't have a curl. So all they do is pretty much push the surface up and down and then decay in a simple way away from that. Okay? Everybody on board with those physical ideas? Okay, so are there any other questions about the math bit before we talk a little bit about where these things come from and what kind of other bits and pieces? And I don't think that I certainly don't expect you to grasp all this math at this stage, but if you wanted to write your paper about this kind of waves, like it's not hard to take an hour or so and walk through these steps and get yourself there pretty comfortably. This is in the linear wave dynamics, it's pretty straightforward. It's a lot of just kind of like plugging in and taking derivatives and making sure it all makes sense. But it's not the physical principles we have already put in place here, that this is the surface boundary conditions that drive the game, and what do they look like? They have to do with this vertical motion of the surface and the pressures on the surface. Okay, so sometimes waves, by the people who study only surface gravity waves, and so they just call them waves, not surface gravity waves, they then refer to them based on where they came from. So wind waves are the most common kind of waves, and they come from the wind. So when the wind blows on the surface, it's kind of hard to, when there's no waves at all, it's kind of hard to figure out how the wind would make a wave start. So let's not worry about that one. But if you had a little wave there and you blow the wind on it, the upwind side of each wave is going to get a little more force than the downwind side as the wind bangs into it and then flows over it. And so that will tend to make the wave get a little bit of push, which will make it put a little bit of energy and momentum into it, and it'll grow a little bit. So when waves are propagating downwind, they tend to grow in magnitude. So that's how wind waves work, basically. There are complicated aspects of how different wind waves all superimpose on top of each other and which wavelength is preferred by what speed of wind and all kinds of stuff like that. There's a lot of complexity in how it works, but the basic idea is you can put energy from the wind into the waves by basically pushing on the back side of the wave, on the upwind side of the wave, and more than you push on the downwind side of the wave. And eventually, the waves will be propagating at the same speed as the wind, and then they don't get any more force. And so you can imagine that they would eventually become what's called fully developed, and they stop getting any more energy. They just kind of cruise along with the wind, and they're happy. Okay, a tsunami or a seismic wave is a surface gravity wave that's forced by seismic activity, which might be an earthquake, might be a mudslide. We said that the bottom in our wave system was flat, but you can imagine if you just drop the bottom, the water would rush into that hole, and then it would come out splashing as a wave. So that resulting wave is the tsunami. You impulsively change the bottom boundary condition, and then the wave radiates away from there. But everything about that Poisson equation is still the same. That part of it is still the same, is just as it was for the system we solved. Storm surge is another type of surface gravity wave, but it's forced by the low pressure system that travels along with a cyclone. So a cyclone is a low pressure in its center. It's true in the atmosphere as well as the ocean. So if our pressure at the surface was one of our boundary conditions, if the atmosphere has, say, 100 millibars low pressure, the water underneath it is going to experience a pressure anomaly. It's going to get sucked up into that hole. And so storm surge is the response to that low pressure that's moving along with the system. It's not quite as clean as that because normally it's any waves that are related with this So there's some wind waves that go along with the storm as well. So it's a little tangled up how the two work together. But that's one of it. And then tides are a combination of surface gravity waves. We're going to spend a whole day talking about tides. So we have more about the forcing. But basically it's because the moon and the sun are changing the gravity that's being experienced by that. And so if we go back to look at our equations, we can change gravity and make a wave. We can change the sea surface height by lifting up a little bit of the surface. We can change W at the bottom by making a mudslide and causing a tsunami. Or we can change the pressure, which is the matching condition for this guy, by having a storm surge. So we're basically playing games by forcing one of these boundary conditions to change, and then that's causing a wave to get traded off in response. All right. So this is kind of a nice way of thinking about these. So this is the period of the wave down here. And then this is broken down into different sources because they all have different kind of typical periods they force. So tides would force the solar tide and the lunar tide. Basically, it's waiting for the Earth to spin. So they're around 24 hours. And then there's the semi-diurnal tide, which is when you get pulled toward the moon when you're closest to it, and the Earth gets yanked out from underneath you when you're farthest from the moon. So you actually get 2 tides per day, not 1. And then a tsunami might be in a kind of 1,000-second time scale. A siege, which is like a burst of the wind driving like a sloshing motion. This usually happens in more like lakes. That might be in 100-second. Or there's a infragravity wave, as sometimes these are called that. And then here are the wind waves, which are in the 10-second to 1-second territory. So if you sit at the beach, just think about it right now and go, like 5, 6, 7, 8 seconds, depending on how long they are, right? And then capillary waves, little teeny tiny waves that are forced by very small wind events. Those are in the kind of 100th of a second territory, little tiny guys. So if you have a storm or an isolated bit of wind, you would have small waves, and then they're gaining energy. They might get fully developed, and then the storm ends, but the waves are still going and cruising off. So remember how we said that swell might be from a storm on the other side of the ocean. So once the wind dissipates or does its own thing, goes off in a different direction, those waves will keep propagating. And waves are actually very, very weakly dissipated. So once they have become swell, they can propagate all the way around the world before they break on a beach. They don't dissipate themselves very much. Oh, all right, how about breaking? So, if C naught is equal to square root of G times H, and a wave is in really shallow water, so suppose here's a wave. Suppose this is only 1 meter deep, and this is 4 meters. And the speed of the wave is square root of G times H. So if H over here is 1 and H over here is 4, what's happening in that? What does that little simple equation predict? Which part of the wave moves faster? The 4 meter should be going twice as fast as the 1 meter if this formula holds in that limit. It does hold in that limit. We actually we have not gone through the math to do it. But you can actually show that this is not a bad approximation even when the waves are in very shallow water. So this part of the wave overtakes the other part until it tumbles and starts breaking. So the crests overtake the troughs when you're in shallow water. And it tends to happen, so the wave will get steeper and steeper, and they'll overtop if they get steep enough. Oh, this is actually showing a different effect of wave breaking. Sorry. This is wave breaking as you go into shallow water. Waves will also break if they get too high on their own, if they get too tall, versus they'll just topple over from a kind of a similar effect. If this gets too tall, it'll tumble instead of going. That can even happen even in deep water. Fully developed waves. I don't know if we want to talk about this. Basically, if the wind blows for a long time in a certain direction or over a certain distance, called the fetch, like so the wind is blowing on the water, you expect to get waves of a particular height out of that, and an average wavelength out of that, and an average period. So if you have 2 hours of wind blowing over a 19-kilometer body of water, which might be typical, blowing here down the bay, you'd expect to get 1 foot waves, and they would have a wavelength of about 8.5 meters and a period of about 3 seconds. Whereas if you're in the Southern Ocean and you blow for 3 days at over thousands of kilometers, then you expect to get 200-meter long waves, 14 seconds, and they're 15 meters tall. So this is fairly typical in the Southern Ocean. This is fairly typical in Narragansett Bay. You don't ever get 15-meter winds in Narragansett Bay because you don't ever have enough room of the wind blowing and making the waves get bigger and bigger. Does that make sense? Okay, so we talked about this a little bit. So the wave interference, if you have 2 different waves, so one of the cool things about this equation is this equation is linear. So I can take 2 solutions to this equation, add them together, and it's still a solution to this equation. So I can take one wave going one way and another wave going another way, or one wave one period, another wave another period, add them together and get a superposition of the waves. And if they're both having crests together, then the crest will add to the crest. They're both having troughs together, the trough will add to the trough. So you get an interference pattern. So the red one is one frequency of wave, and the blue one is a slightly lower frequency wave. And when they're adding together, you tend to get positive. If they're out of phase, you get cancellation between them. And then when they're adding together, you get this. And we saw this in the 2 wave packets superimposed as it was evolving. There was some constructive and destructive interference as it was. So this is called constructive. This is called destructive interference. That's called constructive. Yeah?
Does that affect wave breaking?
It does, because the wave breaking is really about the height, the steepness of the wave at the crest. And so if you put 2 different period waves together and make one crest that's really tall, it'll actually break. So breaking can be triggered by a superposition of 2 waves that wouldn't break on their own. So you have one wave that would be stable doing its thing, another wave, you put them on top of each other and you might make crests that are tall enough to break.
You get that from a single non-dispersive wave that sort of breaks into parts and then the peaks line up.
So a non-dispersive wave, yeah, you could have it either in a dispersive wave case or non-dispersive. So in a non-dispersive case, you might have 2 packets coming from different directions superimposing.
But they'd have to be coming from different directions.
Right. If they wouldn't, one would never catch up with the other one if they're coming from the same direction. If they're non-dispersive. But if they're dispersive, you actually would expect the long waves to overtake the short ones, and as they do, periodically have constructive interference and get bigger crests. So
from the same sort of non-dispersive waves, you could have sort of repeating breaking waves further away.
yes. So you could trigger breaking with 2 non-dispersive wave sources that are adding up in the same place, or you can trigger it from one dispersive wave case. It'll get triggered with this constructive and destructive interference. And the perfect cancellation case where you have 2 waves of the same wavelength traveling in opposite directions is a standing wave, which we talked about last time a little, and that just looks like this, where when there's constructive interference, you get a standing trough, a standing crest, and then you get a standing trough. And it doesn't look like the wave is propagating, it just goes up and down. And it's because if you do your trig right, you can figure out that the combination of a leftward traveling and a rightward traveling just gives you a cosine stationary in space times a sinusoid in time. So here's a picture of a rogue wave. These are not pictures of rogue waves are extremely uncommon because rogue waves are extremely uncommon. But here's an enormous wave. So, I don't know, it's hard to judge by the size of the, 6 meters maybe, 5 meters, something like that, off the side of this boat. But look around it. It's not in rough water. There's just one of them. So it's this crazy thing that there's just one crest that comes cruising in, and they managed to get a picture of it that time. And so the rogue waves are not so well understood, but the idea is they start off as some kind of constructive interference pattern, and then they become nonlinear and have a more interesting wave dynamics than what we've been able to talk about. Something that they start to behave like something that's called a soliton, which is a balance between the nonlinearity and the dispersion. So the nonlinearity is tending to steepen the wave, and the dispersion is trying to pull it apart, and they come into balance, and then that structure could be stable for a long distance. All right, and then the waves when we get to the beach are shoaling. So what happens if the group velocity, if the phase speed is square root of GH, what happens as h gets small? Velocity gets small, so the waves are going to pile up essentially because they're going to converge in their wave speed as they come to shore. So when they pile up, their energy is going to have to pile up, and in addition, they're going to be in shallower and shallower water. So more and more of that energy is going to have to be exhibited as a sea surface anomaly. And so they pile up, they get steeper, they get closer together, and then they start breaking. So as you get into shallower water, the wavelength shortens and the wave amplitude gets taller, both of which tend to make them steeper, and then they tend to break. So this is just that same picture where what if the crest is overtaking the trough? You lead to something that looks qualitatively like a breaking wave. I don't know, maybe we want to talk about the refracting and standing we see. So we've got a lot of things. The seagull knows. All right. So then there's another crazy thing, which is that the orbital velocities do go around in a circle, but if you advect a little hunk of the water with the orbital velocity, it doesn't actually get back to where it starts because the velocities are a little bigger at the top of the loop than they were at the bottom. So they go in these kind of spirogyra patterns, meaning that there's a mean drift associated with the orbital velocity. So that mean drift is called the Stokes drift, and this is an important relationship between these kind of waves and currents. So this is effectively a wave-driven current that goes along with the waves. And so this is sort of a next set of things to worry about. But what it means is if you're sitting on the surface, so look at this parcel, this is tracking just a water parcel, it doesn't go as fast as the wave. The wave goes through it. How is that possible? We talked about this last time. What's the difference between a wave and a current?
Wave doesn't transport the underlying medium.
Yeah.
Does
So
that make this not a wave?
no, it's kind of a blend of both. This apparently is transporting the underlying medium, but it's not transporting it as fast as the wave is propagated. So this is kind of a wave-driven current. Like a Stokes drift is kind of somewhere in the middle, but But the main point here is that if you put something on top of this and it follows this Stokes drift, the waves will pass right by it. So this funny textbook that I have talks about this is that the seagull knows. So the seagull knows not to panic when a wave is coming. The seagull just rides it out and doesn't go anywhere. So the waves go by and the seagull is just sitting there and not worrying, not having to swim to stay on stream. The seagull does have to swim to fight the Stokes drift, but the Stokes drift is not as fast as the wave propagation itself. I know the seagull knows is a strange thing. So waves can refract, they can reflect, they can do all kinds of interesting stuff. Oh, this is kind of a cool one, actually. So imagine that waves are coming in an angle to the beach you're on. What does this say about this, the speed of this part of the wave versus the speed of this part of the wave?
The closer part is slower.
The closer part is slower, which means that they're going to start straightening themselves. So waves can come with a little bit of angle along the shoreline, but it is all essentially guaranteed to be less of an angle at the shoreline than it was offshore. So this is a really fun thing to watch when you go to the beach. You see the waves coming in like this, and then suddenly when they get to the shore, they're much more parallel to the shoreline. And sometimes, if there's a sandbar, you can actually see it offshore. They'll straighten offshore. Even though you can't see the sandbar, the waves are just coming in, and then they get straight, and then they come farther in, because they've been adjusted. And so this is a good example of waves are coming and wrapping themselves around this headland and coming in, you know, almost perpendicular to where they were coming at, where they started out. And if you send them through a chain of islands, then they'll refract as they come around, and then they'll have constructive and destructive interference behind the island. So, sorry, this is not a very good picture, but here's a breakwater and here's another one, and you can see that there are crazy patterns piling up in big breaking waves aligned on the back side of those objects because of the constructive and destructive interference of the refraction. So if you're not careful when you design a harbor, the person who's got their mooring right here might be really unhappy with you because you can make it so that the waves are much bigger here than they were out there. You did it exactly wrong. Oh, an example of the tsunamis. So there have been a lot of tsunamis recently in the news. They're really, so they go really fast. How do we know they go really fast? So they're in, say you're in the open ocean. How deep is the open ocean? Very, like 4 kilometers, right? So if you're in a 4 kilometer water and the bottom drops out 100 meters, you've got a lot of energy. You've got equivalent of a 100-meter wave, and because it's the bottom that's moving, it's going to be like a shallow water wave, not a deep water wave, because it's the whole water column that rushes in to adjust. So a shallow water wave in 4,000 kilometers of water, 4,000 meters, what's that? 10 times 4,000 meters squared per second squared. 1, 2, 3, 4. 200 meters per second. So how fast is 200 meters per second?
100 miles an hour.
Yeah, it's like airplane fast. So when a tsunami goes, they go very fast. So here in the 2004 tsunami in Thailand, it went from Thailand to Africa in about 7 hours. So it crossed the whole of the Indian Ocean in under 10 hours, which is pretty crazy. The biggest effect is right near where you are, because as you're spreading out, like the energy is dissipating some. You know, it's like a point source that's spreading out in 2 dimensions. So the biggest damage is local, but you can, it can be concentrated into, so tsunami, the word tsunami actually means harbor wave, and it's because they can be concentrated when they come into a harbor. So they can really kind of like accelerate in a small basin. We'll talk more about this when we talk about tides. If you force a wave that's very happy, resonant with the chamber it's in, it's sort of like pushing a person on the swing at the same period that they're oscillating at. Their amplitude gets bigger and bigger. So if you take a wave with the right frequency mix, right period, that it would resonate with a particular harbor, it will be greatly amplified as it comes on shore. And so it will have an enormous, bigger signature inside the harbor than it did in the open ocean. So frequently, tsunamis will be maybe 10 centimeters or so out in the open ocean, but then they'll be 10 meters when they get into a narrow harbor. And they'll rise up to concentrate all the energy. Speaking of that, here's the Japan one, the 2011 one. So it took about 9 hours to get to California from the earthquake. So it is as fast as an airplane flying across the Pacific. I mean, it's crazy fast. And this is showing the amplitude as it goes along. And I don't understand why this is a stripy pattern, but they're funny sort of beams of intensity that came out of it. So this one is, these red colors are 20 centimeters, and that purple ring is so that's a meter, and the black ring is 2.5 meters, but in certain parts of Japan it was like 10 meters. So it depends a lot, and as it spreads out, the amplitude is going down, and as it goes into deeper water, the amplitude is going down. Okay. All right. So now we can look at some waves. Very peaceful. Good sound. Oh, I don't know the sound turned up. So can you see short waves? Can you see long waves? You see shoaling and breaking? There's a nice breaker. So you can see as you get into the shallows, the waves start breaking and stuff. They're able to feel the bottom. That's the shoaling part. And so all of these waves in this part are all shallow water waves, but out there, they would be deep water waves when they're far enough offshore. You can watch one of these too. These are always so disorienting because you can't tell like how big anything is. When you have the person for scale. So that's a very big wave. So they have to get towed by the jet skis because you can't swim fast enough to catch up with the wave that are this long. Made it. That's crazy. You have another wave. The most extreme. These are ridiculous. Here's person anyway. You see those and you're like, that would be crazy. And then here come the people. So again, getting towed by a jet ski because these waves are so fast you couldn't possibly catch it. See how much he's cutting across the face of the wave, so he's got to be going really fast. Because it's the phase speed, not the phase velocity, so it's faster to cut across. I think these are in Portugal, this particular one. All right, the last thing to talk about is you can also have waves, internal waves. So waves, if we have a density interface between light water on the top and heavier water on the bottom, you could have a wave not on the surface of the ocean, but on that interface between the light and heavy. Those are called internal gravity waves, and you can think about them a lot using the reduced gravity wave system that we had before and treating it like shallow water equations and going through and doing all the bits. So this is a fun thing to think about. Oceanographers love these kind of waves for lots of reasons, but we don't have enough time to really talk about them in great detail. So I will leave them aside for now. But they do all kinds of weird things. Winch talks a lot about them. All right, cool. Next time we're going to talk about large-scale waves. So we're going to bring the Coriolis into this whole story and see how that changes things around and see what Coriolis effects does.